This presentation is delivered by the Stanford Center for Professional Development.
So today, we're going to continue our discussion of the higher dimensions. We're going to continue our trip into the outer reaches and talk about getting to know your higher dimensional Fourier transform. And the main point that I started to make last time, and I want to repeat, is that you already know your higher dimensional Fourier transform because you know your one-dimensional Fourier transform so well. All right. The point, so this is getting to know your higher dimensional Fourier transform, your. And as I said, you know it. All right? You have to convince yourself of that. There are differences, and I'll highlight some of those differences a little bit today, but even more so next time. But again, the point of using the notation that we've used and the approach we're using is to make the higher dimensional transform look as much like the much like the one-dimensional transform as possible. All right? The formulas carry over, and we'll start to see some of those today. The ideas carry over. There's no reason to think of it as a completely different subject. So let me remember the definition here. Let me remind you the definition and the elements that enter into it. So you have a spatial variable and a frequency variable, and then a transform and a function and a transform from one domain to the other domain. So I usually write the spatial variable like this. So it's a spatial variable. We have the frequency variable, which I call xi, xi1 through xn, same dimension. All right, and we have a function, a scalar valued function, can be real or complex, but it's not vector value. All right, so it's a real valued function or a complex valued function. Then its Fourier transform as a function of the frequency variable is defined by this integral, which we try to make look as much like the one-dimensional case as possible. You integrate all over space, e to the 2 pi I minus 2 pi I x dot xi f of x dx. And even making it look as much like a one-dimensional case as possible, I'm sorry, I still couldn't fit it all in one line. Doesn't look so good. Let me write it over here again. So the Fourier transform of f at xi, I'm just going to rewrite it, is the integral over all space e to the minus 2 pi I x dot xi f of x dx. The new feature here is the vector, is the dot product. All right, you take the dot product of the two vectors x and xi, and that gives you a scalar, and you take the complex exponential applied to that. And writing it in this way makes it look, as I said, as much like the one-dimensional case as you can make it look. All right, and we'll even see that the formulas look very similar, and even the approach to proving the formulas is also very similar. Now, I do want to follow a similar path to what we did in the one-dimensional case. That is, looking at specific transforms of specific functions. I'll do a little bit less of that. And then also looking at general formulas, the versions of the shift theorem and the stretch theorem and so on. I'll do also maybe not quite as much of that as I did in the one-dimensional case where we saw it in more detail. But there, actually, it's in the general formulas that you start to see a few differences that crop up between the one-dimensional case and the higher dimensional case. That's where actually some of the interest is. But let's do a couple of specific examples first of computations. There's an important class of functions for which you can compute a higher dimensional transform by computing a series of lower dimensional transforms. All right, there's a class of examples for which you can compute a higher dimensional transform via one-dimensional transforms. Or at least lower dimensional, maybe I should just say lower dimensional transforms. Typically one-dimensional transforms. And what I'm thinking here are so-called separable functions, what are sometimes called separable functions. I don't think there's a uniform term to describe them, but let me give you an example here. These are separable functions. And they come up often enough that there are enough examples of them. They come up often enough in applications that it's worthwhile actually just calling attention to them. So for example, the easiest example, an important example, is like the two-dimensional. Let's just do this in 2 dimensions, all right? But you can do the same thing in higher dimensions. So let's work in 2D. Then one of the most basic examples and important examples is the two-dimensional rect function. All right, so let's take the 2D rect function. So that would be, I'll call that pi of, or rectangle function of x1, x2. And the graph would look like the two-dimensional version of the graph of the one-dimensional rectangle function. That is to say, see if I can draw this picture of this thing here. So here's the x1, x2 plane, all right? x1, x2, and it's a box, all right? It's a box. Oh, this is one of those, like, you know, IQ tests. Can you draw this box? Answer obviously is no. It's the function which is 1 over a rectangular region in the plane. There we go. Very good. Yes. Yeah, there we go. Perfect. That's fine, Mr. Osgood. Now try doing this basket for us. Okay. All right. It's supposed to be it's equal to 1 over this box in the plane. And it's equal to 0 outside the box. Let me try not to draw perspective here. So here's the x1, x2 plane. All right? And here's the box that goes from -1/2 to +1/2 in the 2 different directions. And the two-dimensional rectangle function is 1 over that box and 0 outside the box. And you can decide, depending on your religion, what you want to do on the boundary. All right? So it's, say, equal to 1 if x1 in absolute value is less than 1/2 and x2 is less than 1/2, and it's equal to 0 otherwise. All right? Now, that's fine. You can write down the formula that way. You can write down the definition that way, and that generalizes the one-dimensional rectangle function. What's not so obvious, that's a really pathetic drawing, isn't it? What's maybe not so obvious is that the two-dimensional rectangle function can be written as a product of one-dimensional functions. That's the point I want to make. All right? So you can write the two-dimensional rectangle function as a product of 2 one-dimensional rectangle functions. In fact, it's easy to write, and I will let you convince yourself of this, that it's just the rectangle function of the one variable x1 times the corresponding rectangle function of the variable x2, the ordinary rectangle function. So this is 1 between x1, if x1 is between -1/2 and 1/2 and 0 otherwise, and this function is 1 if x2 is between -1/2 and 1/2 and 0 otherwise. And if you take the product of those 2 functions, that describes exactly this condition. It's equal to 1 if both functions are, if both variables, x1 and x2, are between -1/2 and 1/2, and it's equal to 0 if either one is outside that interval. All right? All right, if either one, x1 or x2, is outside the interval from -1/2 to 1/2. All right, now not all functions can be decomposed this way, but when you can decompose a function this way, then it's easy to compute the Fourier transform. And it's something to watch for. And again, it happens often enough that it's worth calling attention to it as a sort of special case, important special case. Because now you have the Fourier transform of f at xc1, xc2 is equal to, by definition, so I'll write it out in coordinates, the integral from -∞ to infinity, -∞ to infinity, e to the minus 2 pi I x1 xc1 plus x2 xc2 times pi x1 x2 dx1 dx2. All right, that's just the definition of the Fourier transform. It takes the entire damn board, and that's only 2 dimensions. But now, you can split the variables up. All right? That is, you can write this as, matter of fact, let me combine two steps here. Complex exponentials, or the exponential function being what it is, you can split up that inner product in the exponent to be minus 2 pi I x1 times c1 times e to the minus 2 pi I x2 times c2. And then, as I just pointed out, the rectangle function itself can be written, the two-dimensional rectangle function can be written as the product of two one-dimensional rectangle functions, dx1, dx2. And now you should sort of look ahead a little bit and see what happens. Things decouple. Okay? Things decouple. The x1s and x2s are independent. That is, you can write this as the product of two integrals, which are then actually just one-dimensional Fourier transforms. So this is equal to the integral from minus infinity to infinity, e to the minus 2 pi I x1 times c1 times pi of x1 dx1 times the integral from minus infinity to infinity, e to the minus 2 pi I x2 times c2 pi of x2 dx2. All right? We've done this many times, really going the other way. We've done this many times in a variety of circumstances, taking the product of two integrals and converting that to a single double integral. Here, I'm going the other way around. I'm taking the double integral, and because the variables are decoupled, I can write that as the product of two single integrals. All right? And now you just recognize this is the Fourier transform of the rectangle function. This is the Fourier transform of the rectangle function, but you have to pay attention to what the variables are named. All right? That is, it's the product of, so what do you get for the first one? You get the sinc function of c1, because I'm taking the Fourier transform with respect to x1, and the dual variable here is called c1. And then in the second integral, it's the Fourier transform of the rectangle function again, but the dual variable, the variable here I'm integrating is x2, and the dual variable in the frequency domain is c2. So it's just the product of the sinc functions as sinc c1 times sinc c2. Toy boat, toy boat, toy boat, toy boat. Any other tongue twisters we can try? It's probably the best Fourier transform tongue twister I know, actually. Sinc c1 times sinc c2. Okay. Now, and you can look at the notes. Sorry for a picture of that. It's not. It's you get a nice picture of the product of two sinc functions. Okay. We were able to do this because, so again, we were able to rely on our one-dimensional knowledge to get a two-dimensional result because the function was separable, and that happens often enough that, as I say, it's worth pointing out. So in general, what is the situation? In general, if you can write a function of n variables, and you can't always do this, I want to emphasize this, all right? You can't always do this, but in some cases you can. If you can write it as a product of functions of one variable, or at least functions of a lower dimension, say f1 times x1 times f2 times x2 for some functions. I'm not saying that there's a procedure to do this, for doing this, and I'm not saying that it's always possible. It's not always possible, and there's not a procedure to do it. But when you can, then the Fourier transform of the function of several variables can be written as the product of the Fourier transforms of the functions of one variable. So if you can do that, then you can write, and I won't derive this, the Fourier transform of the big function at the big frequency variable is the product of the Fourier transforms of the little functions at the single frequency variables. Fourier transform of f1, the Fourier transform of f2, c2 times cn. Okay? And there are various combinations of this. I mean, maybe you can write it as a function of one variable times a function of two variable. If it's a function of, if f is a function of three variables, say, x1, x2, and x3, maybe you can decompose it as the product of a function of two variables times the product of a function of one variable, or whatever. I'm not saying that there's any blanket thing that's going to work, or that you might expect to happen, but it is the sort of thing to look for. Okay? It is the sort of thing to look for. And that's what I mean by separable function. Let me give you another example, actually, that will lead to another important class of functions. So we'll handle it one way, then we can also handle it another way. So another example, and I'm just going to do these. Most of the examples I'm going to do just in 2 dimensions because I can't write out. I don't have the patience. I don't have the strength to write anything out in higher dimensions. So another example is the 2D Gaussian. All right. The 2D Gaussian would be something like, I call it G. Say G of x1, x2 would be e to the minus pi x1 squared plus x2 squared. Okay? And again, if you drew the graph of that as a surface in space, and I think the graph is drawn in the notes, you'd see a 2-dimensional like bell-shaped curve, or bell-shaped surface, I guess you'd call it. All right? Now, that's also a separable function because, and in fact it's a product of 2 1-dimensional Gaussians, again, just because of the property of the exponential function. Exponentials being what they are, you can write this as e to the minus pi times x1 squared times e to the minus pi times x2 squared. All right? So it's a product of 2 1-dimensional Gaussians. We'll call that g1 of x1, g2 of x2, although it's really the same function in both cases, where g1 is e to the minus pi 1x squared, g2 is e to the minus pi 2x squared. All right? So the Fourier transform is the product of the Fourier transform of the 2-dimensional function is the product of the Fourier transform of the 1-dimensional function. All right? So the Fourier transform of g at c1, c2 is the Fourier transform of g1 at c1 times the Fourier transform of g2 at c2. And we know what happens if I take the Fourier transform of the Gaussian, you get it back. All right? That's the remarkable property of the Gaussian. That's equal to e to the minus pi c1 squared times e to the minus pi c2 squared. All right? That's fine. But now, actually, the nice thing is, so that uses the separability. All right, now you can recombine these. You could leave it like that. That's a perfectly fine answer. But a perfectly finer answer is to recombine. That is, write this as e to the minus pi c1 squared plus c2 squared. Again, exponentials being what they are. And you're back to where you started. Okay? That is, the Fourier transform of a 2-dimensional Gaussian is another 2-dimensional Gaussian. So f of g c1, c2 is equal to e to the minus is itself c1 squared plus c2 squared. Cute, huh? It's nice. It's nice. So again, our 1-dimensional knowledge, our 1-dimensional expertise, in this case, lends itself to understanding a higher dimensional phenomena. And you could do the same thing in higher dimensions. You could have a higher dimensional Gaussian. All right? And you know, it makes there certainly you can imagine, you should be able to imagine instances where you would want to consider higher dimensional Gaussians. If you think of the Gaussian, the bell-shaped curve is describing the distribution of a set of measurements, all right, then instead of taking one measurement, you're taking many measurements. You know, and they can be distributed normally, so distributed according to a higher dimensional Gaussian. That's okay, all right? And so you'd want to know the higher dimensional Fourier transform of the Fourier transform of a higher dimensional Gaussian. And of course, you know, you have higher dimensional versions of the central limit theorem and all that stuff. All right, it all carries through. And it all carries through pretty much the same because you can make the higher dimensional case look like the 1-dimensional case. All right, you're not seeing any essentially new phenomena. They're the same sort of things that come up in higher dimensions have already come up in 1 dimension. That's the power of this approach. Okay? Now, one of the reasons why I wanted to do the Gaussian is because not only is the Gaussian separable, the Gaussian actually has another property that is an illustration of another important class of functions that come up a lot in applications, and so consequently there's sort of special things you can say about them as far as the Fourier transform goes. Namely, the Gaussian is radial. All right? So the Gaussian is also an example of a radial function. All right? Now, by that I mean if you introduce polar coordinates, there's certain circular symmetry to the Gaussian. So if you introduce polar coordinates, That is r equals the square root of x squared plus y squared, or r squared is equal to x squared plus y squared. And theta is equal to arctan of y over x. Or going the other way, x equals r cosine theta, or I should say, let me use x1 and x2, not x and y. Sorry, let me be consistent here. x1 squared plus x2 squared. Sorry, I'll get it out of the way in just a second. x2 divided by x1, or let me write it over here. So I'm introducing polar coordinates in the x1, x2 plane. So x1 is equal to r cosine theta, x2 is equal to r sine theta. Then, of course, the Gaussian is just e to the minus pi r squared. It depends only on r, the radial distance from the origin. E to the minus pi x1 squared plus x2 squared is e to the minus pi r squared. All right, that's what you mean when you say it's a radial function, is if it depends only on r. In this case, it depends on r squared, but the dependence is on the distance from the origin, not on x1 and x2 independently, so to speak, but only on x1 squared plus x2 squared. Okay? Okay, so this is there, so it depends only on r, not on, let's say, x1 and x2 independently, if you know what I mean. Well, I mean, I'm sort of caught in a language here, independently. I sort of put quotes around that because from what I just said before, it's separable if it depends on x1 and x2 separately, but not independently, okay? Sorry for the clash of language. I don't know how else to say that. All right. Now, this is something that comes up really in 2 dimensions or in higher dimensions that wouldn't come up in 1 dimension. In 1 dimension, you have only one variable, right? One variable is describing the position or the time or whatever, but in space, it's a little bit different. You have a little bit more freedom, all right? You have 2 degrees of freedom instead of 1 degree of freedom, all right? So it makes sense to consider a class of functions that depend only on, say, for example, the distance from the origin. Those are the radial functions, all right? You don't see that in 1 dimension. So radial functions in general depend on the distance r from some origin. I mean, you can fix the origin. All right, and you've seen many examples like this. They come up all the time in applications. And the important thing is, as far as Fourier transforms are concerned, is that the Fourier transform of a radial function is also a radial function. That's what I want to show to you. All right. Now, let me write it over here. So I want to see, and this is actually a little tricky. Okay. The Fourier transform of a radial function is also a radial function. Radial function. All right. Now, as I say, this is a little tricky, and there are actually a lot of interesting things to say around these ideas. Let me just, I don't think we're going to be able to get into this, but let me just make a comment here. We're going to get a somewhat complicated formula for the Fourier transform of a radial function. All right, so we'll get a formula for this. We'll convert the usual definition of a Fourier transform into a radial version, into a radial Fourier transform. Again, I'll sort of put that in quotes. It has another name. You call it the Hankel transform. Now, in many applications, radial functions are a more natural way of describing the phenomena. And the problem is that the Fourier transform, as it's given, the definition of the Fourier transform is a very Cartesian thing. All right, I'll say this more precisely when I actually write down the formula for it. But I just want to set the stage here for something that we may not, or I just want to mention something we may not have a chance to talk about, but you should be aware of. So we're going to get a formula for this. Fine, it's going to be a little bit more complicated. The reason why, and this causes all sorts of problems in a lot of applications, because the Fourier transform itself is set up in sort of a Cartesian form. All right, it's sort of the definition involves an inner product, and the inner product somehow looks very Cartesian. Consequently, the discrete Fourier transform and the algorithms for evaluating the discrete Fourier transform are also very Cartesian in nature. It requires to implement a discrete Fourier transform and the algorithms that go with a discrete Fourier transform for 2 dimensions and higher dimensions requires that you put down a Cartesian grid. All right? But in many cases, the functions you're interested in don't fit naturally on our Cartesian grid. They fit much more naturally on a polar grid. All right? And you don't have analogous formulas for the discrete Fourier transform and for the FFT algorithm for polar grids. And it's a problem. Where is it a problem? Well, one big area where it's a problem is medical imaging, where the way you take samples and the way you actually work with your functions is much more naturally described in polar coordinates than it is in Cartesian coordinates. And you want to do a lot of serious computation, but it's not set up for it. All right? It's not set up for it because the formulas somehow, on the one hand, the fast algorithms, the efficient algorithms are all set up in the Cartesian world for rectangular coordinates, and the phenomena that you want to compute are much more naturally described in polar coordinates. And there's a problem. All right? You have to sort of, and you have to, it's a hack job to get around it, actually. I mean, there's not really a good, I don't know, I may not know the state of the art, but at least I believe that it sort of has to be kind of sort of gotten around, but not really dealt with theoretically or really. I mean, there's no way of doing it other than hacking, to tell you the truth. All right, so now let me show you how to do this. Let me show you what the issue is here. All right. So what I want to do is, the only thing I can do is convert the formula for the Fourier transform into polar coordinates. All right, so the formula for, and again, I'm just going to do this in 2 dimensions. So the formula for the Fourier transform is the integral from minus infinity to infinity, integral from minus infinity to infinity of e to the minus 2 pi I x1 times c1 plus x2 times c2, f of c1, c2, oh, sorry, x1, x2. I'll get it. dx1, dx2. All right, so all I want to do is convert this to polar coordinates. You say it's all I want to do, but that's where the complications come in. Now, some of this is straightforward. We're assuming that f is a radial function, all right? So I want to convert to polar coordinates. Now, polar coordinates in both planes, actually, both the x1, x2 plane and the c1, c2 plane. So let me write x1 is equal to r cosine theta, x2 is equal to r sine theta for polar coordinates in the x1, x2 plane. But I also have the frequency plane. So let me introduce polar coordinates there, and I got to call it something else. So I'll call it rho cosine of phi, and c2 is going to be rho sine of phi. All right, same interpretation of polar coordinates, but instead of calling it r and theta, I'll call it rho and phi. All right? And as we will see, the Fourier transform of f, if f is a radial function, meaning that it's a function of r, the Fourier transform of f will be a function of rho. That's what we're going to see. All right, so we'll see that if f is radial, a function of r, then the Fourier transform of f is a function of rho. All right, that's what it means to say that the Fourier transform of a radial function is again a radial function. That's what it means. All right, so let's do this. So part of the conversion is easy. All right, that is f of x1, x2 gets converted into f of r. Right? I'm assuming it's a radial function. All right, so that means it's a function only of r, whatever the formula is. And I know what happens to the area element also. dx1, dx2, the area element gets converted into r, dr, d theta. That's the area element in polar coordinates in the x1, x2 plane. The problem comes in, not the problem, but the sort of, it's more complicated, is in converting the inner product. That's when I say it's very Cartesian. All right, that's what I mean when I say it's very Cartesian. You have to convert the inner product. So x1, what is the inner product? It's x1 c1 plus x2 times c2. So I'll just write this out, all right? It's r cosine theta times rho cosine phi plus, that's x1 times c1 plus x2 times c2 gives me r sine theta times rho sine phi. All right? So the r and the rho factor out of both terms. That's r times rho cosine theta cosine phi plus sine theta sine phi. All right? And if you remember your addition formulas for the cosine, and I'm sure we all do, that is r rho times cosine of phi minus theta. So this is r rho cosine of theta minus phi. Phi minus theta minus phi, doesn't matter. Okay? Okay. So what happens to the Fourier transform? All right, it's straightforward. I should say when I said it's complicated. The complications are actually about to come up. It's sort of straightforward just to plug formulas in and convert just mechanically from Cartesian coordinates to polar coordinates. So what do I get? I get the Fourier transform of f becomes what? The Fourier transform becomes, it's the integral. All right, let me put the limits of integration in. All right, so I gotta put the limits. I gotta have to describe the whole plane. So to describe the whole plane, theta is going from 0 to 2 pi, and r is going from 0 to infinity. I'm going to integrate r d theta dr. Doesn't matter. So what happens to the exponential? It becomes e to the minus 2 pi I r rho cosine of theta minus phi. All right, times f of r times r d theta dr. Do I have it all? Okay, I have it all. All right, that's the formula for the Fourier transform. All right, that's the formula. That's what you get just mechanically converting the two-dimensional Cartesian Fourier transform into polar coordinates. Now you have to work with this a little bit more. All right, so there's something important to notice here, and I'm not going to, it's discussed in the notes, but I'm not going to prove it for you. But here's what you find. You find, here's a fact, that the integral from 0 to 2 pi of, let me just try, I'll make sure I sort of stay with my notes here. So there's an r integral and there's a theta integral, all right? The only part that depends on, the f doesn't depend on theta, that's what it means to be radial. So it's this part here that's depending on theta. But it doesn't just depend on theta alone, it also depends on phi. All right, the angle in the other plane, angle in the frequency plane. So, but the fact is that this integral, e to the minus 2 pi I r rho, cosine of theta minus phi d theta, actually is independent of phi. All right, that's a fact that you can check. You can look in the notes. I'm not going to verify that. It's not hard to verify, but it's one of these things you have to look at and you have to know. Or if you didn't know that, your formula would become you wouldn't be able to make any progress as we're about to. All right, so to say that that's independent of phi means that in fact that integral is the same as if phi were not there. All right, so in fact, the integral from 0 to 2 pi of e to the minus 2 pi I r rho cosine of theta minus phi d theta is equal to the integral from 0 to 2 pi e to the minus 2 pi I r rho cosine of theta d theta. If I just leave the phi out. All right? Now that's just grand. And you see there's no f in there or anything. I mean, it's just in some sense an ordinary integral. All right, it's e to the minus, you know, it's some function of theta integrated with respect to theta. All right, there's no more phi in there. Now the problem is this is not an elementary integral. All right, there's no formula for antiderivatives that's going to allow you to evaluate this integral in closed form. All right, you don't have a closed form expression for this. All right. So what do you do if you're a mathematical jerk at a point like this when you don't have a closed form expression? You define your way out of trouble. You say, well, that just defines a new function. That's what that does. And in fact, that's what's done. You know, it's what pisses engineers off. All right? So define and I'll give you the general definition. Let me write it down here. I got to copy it from my notes because I don't know it off the top of my head by any means. 1 over 2 pi, this integral, this is the integral that comes up, well, let me write it down, then I'll say something about it. E to the minus IA cosine of theta d theta. A is a real number here. All right? And you can see that what I have here is a version of that. I have 2 pi and I have minus 2 pi r rho and so on. All right? This is called, all right, well, so then the integral that I have so we have, what do we have? We have 2 pi times j naught of 2 pi r times rho. That's what we're dealing with here with this integral. Okay? Now, j naught is called the 0th order Bessel function of the first kind. Zeroth order Bessel function of the first kind. All right? Be afraid, be very afraid. There are several terms there that ought to make you afraid. 0th order, that would suggest that there's more than one order, like first, second, third, fourth. And first kind would suggest that there's more than one kind, like second kind, third kind, whatever. And all that's true. All right? There are Bessel functions of many orders and many kinds. All right? They always come up, Bessel functions always come up in the context of radial functions. All right? They always come up. Anytime you're dealing with radial, and so be aware of this. All right? If you're dealing with problems that have circular symmetry, chances are you're going to come across Bessel functions. The other reason for that is often separation of often there are partial differential equations involved that are describing the phenomenon. And often one does a separation of variables and assumes that the solution is a product of an angular function and a radial function. And very often the radial function or the angular function, one or the other, has solutions which are Bessel functions. The equations are of a certain type and the solutions are Bessel functions. All right? So if you were a British student around the turn of the century or in the early part of the 20th century, you would learn all about Bessel functions of every order and every kind. All right? Because that's what all British students had to learn for the competitive exams they had to take. There is a famous book by G.N. Watson called A Treatise on the Bessel Function, which runs to something like, 800 pages or something like that. And the publisher wanted Watson to do a second edition of that book, but he didn't have it in him to do a second edition. There was a second printing, and I think the second printing says something like, since the publication of the first edition, my interest in the Bessel function has waned. One might expect, right? But it's, what can I say? You know, I mean, these sort of special functions of mathematical physics, they're often called, just come up in the applications. Now they're all hardwired into Mathematica and hardwired into MATLAB and things like that, so that you can draw graphs of these things, you can compute with them and so on. You don't have to have somehow the same kind of intimate knowledge that was the terror of British students' lives in the early part of the 20th century. But they still do come up. So now, what is the consequence of this for us? So now we conclude, all right, the Fourier transform of f of r, a radial function, is, I will call it, and we see that it's going to be a function only of rho, not of phi, because the phi is gone. All right, is f of rho is the integral is, all right, I'm going to write it down here, I have to be careful, 2 pi times the integral from 0 to infinity of f of r times this j naught of 2 pi r rho dr. Okay, 2 pi r rho dr. All right, no phi. The phi is not in there. All right, the phi is not in there because of that fact. All right, that this integral is independent of phi. So I skated over that, but that, in fact, that's sort of the whole ballgame. All right, because that says that the Fourier transform of a radial function is also radial. I didn't do anything here except substitute the formula, substitute the definition of j naught for what our inner integral was when I was computing the Fourier transform, and I converted the Fourier transform into polar coordinates. Okay. Now this too has a name. Yeah, you have a question?
Are there?
Yeah.
Before the dr?
Oh, thank you. RDR. Thank you. All right, polar area, polar form for area, RDR. Okay. All right. Now, in fact, this has a name. They call it Bernie. The name of this is, they call it Mohammed. Sorry. This is called the 0th order Hankel transformation. Hankel transform. All right, so again, you can be a little afraid here because if there's a 0th order Hankel transform, you can believe there are higher order Hankel transforms, and I'm sorry to break it to you, but there are, you know. But we don't have to deal with it. So for us, the 0th order Hankel transform is nothing other than the Fourier transform of a radial function, period. All right, and the headline from this calculation is that the Fourier transform of a radial function is another radial function. All right, and that's important in applications. I mean, I'm not just telling you this for the fun of it. All right, this comes up in all sorts of different applications just because radial functions come up in all sorts of different applications, and it's the kind of thing you have to know. All right, you don't have to know, you don't have to be intimately familiar with Bessel functions and all the rest of that jazz anymore, but you do have to know these sorts of things. And you know, and the basic fact you should walk away with is that radial functions go to radial functions under Fourier transforms. Okay? And also the fact to walk away with is, or the thing to be aware of, is that you know, this can cause some complications in the computational side of things, because some algorithms and some sort of computations are set up in Cartesian form, and they don't convert so easily into polar form. All right, so that causes problems. That causes problems. All right. Okay, now, full stop, something new, something different. We're going to have, as I say, sort of a, I'm not going to go through the same hit parade of Fourier transforms in the higher dimensional case that I did in the one-dimensional case. All right, again, because the point is that what you know in one dimensions carries over to higher dimensions. I do want to go over a number how the theorems look, because there I want you to see how both things look similar and how things look different. We don't have much time today, so I don't want to get caught in the middle of something, much more time today, so I don't want to get caught in the middle of something. Let me say a little bit what happens to convolution and then maybe the shift theorem. I may have to say the shift theorem, and certainly the stretch theorem is where something actually very interesting happens that doesn't happen in one dimension. But let me just mention convolution, all right? Because here's something where it looks exactly the same as the one-dimensional case. All right, so let me at least record that fact. So convolution. What is the definition of convolution of two functions? The definition of convolution of two functions can be made to look exactly the same as the one-dimensional case if you write it in terms of vectors. F convolved with g at x is equal to the integral over Rn of f of y, g of x minus y, dy. Okay, that's the same looking formula. Remember, f and g are scalar valued functions here, so that's the ordinary product. I mean, there's nothing special there. Now, you would not want to write this out in coordinates. You are much happier, writing this out in vector form. I mean, think about writing this down in the two-dimensional case. You would write f convolved with g of x1, x2 is equal to the integral from minus infinity to infinity, the integral from minus infinity to infinity of f of y1, y2 times g of y1 minus x1, comma y2 minus x2 dy1 dy2. That's what you would write out in the two-dimensional case. You certainly wouldn't write out the three-dimensional case, right? You wouldn't want to do that. Nobody would. All right? It's so many variables, so much space, so much pencil lead. All right? But that's what it is. All right? That's what it is. It's much easier to write out the definition in vector form. All right? Now, here's something else you would not do. In one dimension, I tried to scare you off this anyway. There's the whole flip and drag way of life, right? The whole flip and drag religion of trying to visualize convolution. Flip this, drag that, screw you, right? Now, you would not flip and drag these higher dimensional functions, all right? Nobody in their right mind would try to flip G, drag F, or do anything else when the graphs of these things are surfaces. The only case you could do it would be functions of two variables where you could visualize the graph as surfaces in R3 in 3 dimensions, and then you might try to think, well, I'll flip this, I'll drag that, I'll move it over the whole plane, and I'll add it all up, and sure, I can do that. That's worth my time, sure. You know, forget it. And there's no way you could do anything like that in higher dimensions. All right? But it is true, so don't do it, but it is true that the standard interpretations we have of convolution still hold. All right? It's just all the operations and all the interpretations of convolutions hold because the form is the same. All right? The form is the same. It can be viewed as a smoothing operation. It can be viewed as smearing out. The good properties of one function are inherited by the convolution. All right? Just don't flip and drag. All right? So in all formulas, properties, interpretations continue to apply. All right, that's good news. All right, in particular, the Fourier transform property still applies. The so-called convolution theorem still applies. All right, the Fourier transform of the convolution of two functions is the Fourier transform of f times the Fourier transform of g. And the Fourier transform of the product of two functions is the convolution of the Fourier transforms. All right, so the basis of signal processing is still with us. All right? All right? Signal processing in higher dimensions amounts to, in many cases, taking the convolution of two functions in the spatial domain corresponds to taking the product of the two functions in the frequency domain. All right? And to do filtering, in particular, now one of the places this comes up, and you have a problem on this actually, is images. All right? We talked about this last time. What is an image? You can think of an image as a function of two variables, x1, x2, where the value f of x1, x2 corresponds to the intensity. Think about black and white images, going from 0 to 1. All right? How do you do filtering? How do you do signal processing on images? Well, most often, you do it by some sort of multiplication in the frequency domain. All right? The spectrum of the image times something, some mask, some filter, all right, that you are cooking up. All right? You take the product in the frequency domain, that corresponds to convolution in the spatial domain. It's not the only way where it comes up, but that's a typical way it comes up. All right? And the fact is, again, the convolution corresponds to multiplication if you take the Fourier transform. Same thing holds. I'm not going to prove it again. It's the same proof. I mean, it's the same argument as before. Really. I mean, you could have discovered higher dimensional convolution the same way we discovered one-dimensional convolution by asking, is there an operation, is there a way of combining two functions which corresponds to the Fourier transforms multiplying? That's what we did in one dimension. You could do the same thing in higher dimensions. Same thing because we've made everything look in the higher dimensional case as much as possible like the one-dimensional case, so it goes through. It's very powerful. All right, it's very powerful. All that hard-won intuition, all those formulas are going to go through. All right, we'll quit for today. Next time, I am going to go through where things are a little bit different. I want to go through the shift theorem, and in particular the stretch theorem. I love the higher dimensional stretch theorem because there's new phenomena that come up that also have very important, actually, physical applications and physical implications. All right? So we'll do that next time.